Okay, folks, so now that we've done a review of both the graphs of the exponential and log functions, and we've looked at the new domain restrictions that we have, and the old ideas of domains and ranges still hold. What's new here is we've said that you can only take the log of positive values. That is, your argument, the stuff inside the logarithm, must be positive. Let's incorporate that into doing compositions of functions and stating their domains. So here, when I look at letter A here, I see two problematic operations. I see the problematic operation of taking a logarithm, and I see the problematic operation of doing division. Notice we're also adding 5. We're also subtracting 3, but neither of those operations are in any way problematic. And so what we want to do is we want to sort of catalog and look at, further analyze each of the problematic operations. So for division, we need the denominator cannot be 0. So that x minus 3 cannot be 0. Why? Because a problematic operation is division. We're not allowed to divide by 0, so that tells us x cannot equal 3. Secondly, and in a way sort of unrelated, we're also doing the problematic operation of logarithms, and we need the argument of the log must be positive. So we need the argument to be greater than 0. Our argument in this case is x plus 5. We need this to be greater than 0, so we need x to be greater than negative 5. And then when it comes time to give the domain of this function, we're going to the fancy math word is we're going to union together these two sets. This is all numbers except that x cannot equal 3, and this is all numbers for which x is greater than negative 5. And if we union those two together, we could give the domain, and let's go ahead and do that in interval notation. The domain of f then would be from negative 5 to 3 unioned with 3 to infinity. So this statement told me that x needs to be greater than negative 5, and notice that's sort of incorporated here, but then we need to pluck out the value that would give me a 0 in the denominator, so we plucked out the number where x equals 3, because that would result in a 0 in the denominator. So here is our domain for this composition of these two functions. Let's look at this problem here. This one's a little bit more difficult. G of x is equal to the natural log of 1 plus cosine of x. So let's ask ourselves, what are the problematic operations? I'm taking the cosine of a number, I'm adding 1 to a number, and then I'm taking the natural log of that. Of those three operations that I just mentioned, only one of them has a restriction to it, and that's the logarithmic operation. So we need the argument of the log to be positive. That means we need 1 plus cosine of x to be greater than 0, which means we need the cosine of x to be greater than negative 1. Well, normally the cosine of x outputs values between minus 1 and 1, and it's only in limited cases where we would result in a cosine value of negative 1. And when does that happen? Well, if you go look at your unit circle, here's our unit circle. Where is the cosine value equal to negative 1? Remember that on the unit circle, we can find the value of the cosine by looking at the x-coordinate of the ordered pairs. And there's only one ordered pair on the unit circle where the x-coordinate is negative 1, and that's this pair right here, which corresponds to, say, the angle pi, but also the angle minus pi, or the angle 3 pi. If I were to go one lap around, there's 2 pi, and then one more pi would land me here. So it's all odd multiples of pi. So if we were to give the domain of this would be the set of x, such that x can be any real number, except that x cannot equal an odd multiple of pi. And that's how I write an odd multiple of pi for in an integer. Let's just test that. Notice, for example, if x were equal to, let's just say x were equal to 5 pi, well, if we were to look at this, the cosine of 5 pi, because it's an odd multiple of pi that lands me over here for this angle, that's equal to -1. And if I added 1 plus -1 inside the argument of this natural log, then we end up with an argument of 0. But we said that the argument needs to be greater than, strictly greater than 0. And so that's why we got this unusual domain for this composition of functions. Let's look at this problem right here. Here we've got a few different problematic operations. We've got a radical, in fact this is a even-powered root, in fact this is a square root, and then we've got the natural log. So let's break it up into various cases like we did before. So for the square root specifically, but this holds for any even-powered root, as long as the index of that radical is even, we need 5 minus x to be greater than or equal to 0. That goes back to this idea that we developed in the last video, that you cannot take the even root of a negative number. So we just set the argument, the radicand of that square root operation, to be greater than or equal to 0, which tells us minus x gives you greater than or equal to -5, or that x needs to be less than or equal to 5. Okay. Now, for this next problematic operation, we're taking a natural log, and we can only take natural logs or any logs of positive arguments. So for the natural log, we need the argument to be greater than 0. So we need x plus 5 to be strictly greater than 0, which means we need x to be strictly greater than -5. Now, I have had students in the past get tripped up with this operation here. Now, the domain of the exponential function is all real numbers. If I look at this expression here, I do see a problematic operation. Let me zoom in on that. I do see a problematic operation. We've got the problematic operation of division. But notice the variable x is in the numerator of this expression. And so regardless of what value I let x take on, there's no way the argument, or there's no way the denominator inside this division problem would ever be 0. So this holds for all numbers x. I can choose any number I want for x and never arrive at a domain restriction if I'm just asking you to give the domain of this function without any prior imposed restrictions. So now I can go ahead and give the domain of h. Let's do that. The domain of h, and I'll do that in interval notation, would be we need x to be greater than -5, and we need x to be less than or equal to +5. So our domain would be from -5 to 5. So something I really want you to pause and think about. Why was this symbol less than or equal to versus why was this one why was this symbol greater than or equal to versus why was this symbol strictly greater than, and how did that show up in the resulting answer to this problem? Okay, so these are good exercises to work, so I'm going to have you go ahead and work these next 3 questions. I'd like you to try D, E, and F on your own, combining a few of these different ideas. I think you'll find that D, E, and F are slightly less complicated than the 3 examples I just worked. So go ahead and pause the video and answer these 3 questions. Okay, now that you've worked those 3 questions, I would like to go ahead and work one challenge problem with you. Let's look at this example right here. In this case, I actually see a total of 3 problematic operations. So pause for a second and ask yourself, what are the 3 problematic operations in this problem? So here are the 3 problematic operations that I see. I see one problematic operation is that we're taking an even-powered root, an even-indexed root, specifically a square root. But it would be the same problem if this were a 4th root or a 6th root, and it would not be a problem if this were a cube root or a 5th root. But we've got an even-indexed root. That's one problem I see. Another problem that I see is we've got the natural log, and we've got restrictions on our natural log function. That's what we're highlighting in this sequence of videos. And then finally, we have one more problematic operation. We have the problematic operation of division. And this is certainly a problem I find that if you don't separate out these 3 separate problems, you will end up making a mistake on this problem. That's why I break it up into just asking myself, what are the domains for each of the individual problematic operations. Okay, so for the square root, we need the argument, or the radicand, needs to be greater than or equal to 0. So we need 9 minus x to be greater than or equal to 0. So minus x needs to be greater than or equal to minus 9, or that x needs to be less than or equal to 9. The next problematic operation is the natural log, and we need the argument of the natural log to be strictly greater than 0, which means we need x plus 4 to be greater than 0, which means we need x to be greater than negative 4. Okay. Now, I've specifically chosen this example, folks, to hopefully convince you of this analytical method. I have had students in the past that have been able to guess domains of functions and get the right answer in a lot of instances without doing this analysis. And the reason why I picked this problem is to try to convince you that eventually you need a more systematic method. And this is the method that I'm trying to get you to learn, where you break this down by the various problematic operations. Okay? And this is certainly one where I've seen students try to guess the domain of this problem, and they almost always get it wrong if they don't do this case-by-case analysis, analyzing each of these problematic operations. Okay, so to that end, let's try this last problem here. For division, we need the denominator. If I'm going to do division, the denominator cannot equal 0. Well, what's my denominator? My denominator is the natural log of x plus 4, and that cannot equal 0. But what I could do here to help me analyze this is, let's go ahead and say then that the natural log function only outputs a 0 when the argument of it is 1. That's a tough idea, folks. That's where I want to go back to this statement right here. Notice that the natural log of 1, or the log base anything of 1, as long as a is greater than 0, log base anything of 1 is equal to 0. So that's a point on any log function with a greater than 1. And so if we're asking the question, as we are down here, what would make the natural log of an expression to be 0? That would happen when the argument comes out to be 1. So that tells us that x cannot equal negative 3. So that might have been a difficult leap to make, folks, so just check me on this. If I were to take negative 3 and plug it in for x, don't worry about what's happening in the numerator. Look in the denominator. If I plug in negative 3 for x, we would have negative 3 plus 4, which is positive 1. But the natural log of 1 is 0. And so when x is a negative 3, that results in the denominator of the expression being 0, and we have to exclude that possibility. So we cannot allow x to be negative 3. So if we were to put together all of these ideas to give the domain of this function, here we say x must be to the right of negative 4. Here we say x needs to be to the left of, or in the same spot of, as 9 is on the number line. And here we say x cannot be negative 3. So putting all of those ideas together, we get that the domain of this function goes from minus 4 to minus 3, unioned with minus 3 to 9. And I think that this is a problem where if you sat there and tried to guess and test what the domain was for this problem, you would be there a long time before you'd arrive at the right answer. Whereas here I'm trying to show you this case-by-case analysis. So folks, this is probably harder than I would ask you on an exam, unless it were maybe a challenge question. But this is the sort of analysis that you're going to have to do when you get to your calculus course, and I want to get you started on that. Okay? But regardless, I think questions like number 4, A, B, and C here, where we again analyzed various cases. We had division, we had natural logs, here we had a square root, here we had a natural log, where we analyzed each of these cases. I think that that's a completely fair game problem. And what I'm trying to get you to do here, folks, is to separate each of these problematic operations and analyze them separately, and then put the 3 restrictions together into a single interval. All right, folks, that was all I wanted to cover in this video. The next thing I want to do is I want to give you some more practice with sketching the graphs of exponential and logarithmic functions. So here I've given you 4 additional problems to work, and I have hyperlinked the solutions. I'm not going to QR code these, so just click the hyperlink solution to check your answer. But please practice this. This involves the transformations of your library functions applied to exponential and logarithmic functions. So give that a shot. You've got 1, 2, 3, 4 of these. So give that a shot and let me know if you have any questions on those. Otherwise, thank you for your patience as we went through this pre-work, and I'll see you next time. Bye-bye.